Hello, pre-calc students. It's Mr. Beck, and welcome to our discussion or continued discussion about what I call the story of functions, which covers 2.1, and we're going to go a little bit into 2.3 as well. So 2.1, the big issues we're going to talk about are domain and how we apply domain. And then in 2.3, we're going to discuss a little bit about the difference quotient and the slope of a secant line versus a tangent line. So to begin, domain of a function, what's important about the domain of a function is this domain is what goes into the function. What are all the different x values that we can put into a function? We want to know what goes in. And just as importantly, we want to know what we're not able to do. So when it comes to the domain, we want to know that what goes in is going to give us a value, then what comes out or what does not go in, so that we know what our limitations are. That's the biggest thing. What can we not do? And then more importantly, why not? Why can't we do it? So for the warm-up 3 that I have here, or this function, the way that I look at all these problems is I identify the function name, and then after I identify the function name, then I say, what is the domain of that function? So for 3a, this is a quadratic function, and the domain of a quadratic is all real numbers. Now, in the past, we've done notation where we've given you a number line, and we ask you to graph on the number line. And graphing on the number line, that's kind of annoying and tedious in my opinion. So what we're doing is we're translating from a number line, we're translating that to interval notation. The interval notation that I have here says what happens, really it replaces what's on the number line. So more importantly, so if our graph goes from negative infinity to positive infinity, this shows that we're starting at the x value of negative infinity and goes to the x value of positive infinity. For part B, 2 over x, this is a rational function, and rational functions have issues when your denominator is 0. So I like to set my denominator equal to 0 and then solve from there, and then solve an inequality. When it comes to this inequality, x is not allowed to equal 0, so if you can tell here, there's an open dot. So with that open dot, the open dot means that we're not going to be able to include it. So with the open dot, what we show is we show these parentheses, and these parentheses are put into place to say we're not able to actually get to 0, but we're going to get very, very close to 0. And so these parentheses, when I get to interval notation, translate to parentheses around the 0. This says that we're going from negative infinity to 0, and then from 0 to infinity. There is a u that we put in between there. That u stands for union. So it's the union or the joining of those two sets together. Then for this is a radical function, and radical functions, really square roots are the main radical functions what we use. What's underneath that square root is not allowed to be negative. I translate that into an algebraic sentence of x is greater than or equal to 0. So when we show this on graphing, you can see that this should be a solid dot right here, but when we turn it into the interval notation, we are going to use a bracket, meaning we're going exactly through that x value of 0. So from 0 to infinity. We have a couple warm-ups. So on 1a, this is a quadratic function. Quadratic functions have a domain of all real numbers. The two notations I have here are the interval notation that you saw. This notation is called set notation, where it's a very specific, or specifically written of the set of all x's. This line means such that x is a member of the real numbers. This is definitely a little bit more formal. I'm okay if you write x as a member of the real numbers or interval notation. I know in my directions I asked for both. I kind of like jumped between them based off of what we needed. On B, an algebraic approach to this problem is we set x plus 2, whatever is underneath the radical, greater than or equal to 0. And if we solve that inequality, we will get the expression x is greater than or equal to -2, which is what I have here. Interval notation is going to model kind of what I did up in 1c there. 3, or c, is a rational function. So if I want to set up an algebraic expression, I could say x minus 3 is not able to equal 0. So x is not able to equal 3. And then here are the two notations for that domain. For 2, this level 2a problem, if I want to algebraically simplify this, I could factor an x out and I'm left with x squared minus 2x. If I do that, I could reduce the x's to this expression here, but the one thing we have to be careful of is we have to maintain that the domain is still not allowed to equal 0. One of the dangers of algebra is if you do enough simplification, you can lose what you started with, or at least the ideas behind what you started with. So x is just not allowed to equal 0, even though it kind of looks like it does, or you're able to. For part B, you can see the algebra that I did here. I set 7 minus x greater than or equal to 0. Solving the inequality, if I divide by the -1, then that means that I'm going to have to flip the inequality sign around. And that inequality sign translates to looking like that in interval notation. For C, x squared minus 4 is not allowed to equal 0. It's not allowed to equal 0. So x squared is not allowed to equal 4. Now, something that I want to point out here, if I take the square root of both sides, we mentioned on day 1, the square root of x squared is actually the absolute value of x. So the absolute value of x is not allowed to equal 2. The absolute value is a piecewise where one piece has one function, one piece has another function. What that turns into is officially positive or negative x is not allowed to equal 2, so x does not equal positive or negative 2. I am very well aware that most students will go straight from here to here, and I have no problem with that, but I wanted to show a little bit of proper mathematics. For 3a, we get a little bit more complicated with the level 3 problems. So we start by factoring. We factor out the 3x, and we get 3x is not able to equal 0, which is how I get that part of the domain. And 1 minus 3x is not able to equal 0, where if I solve that, 1 minus 3x does not equal 0. Negative 3x does not equal 1, so x does not equal -1/3. And that's a positive 1/3, excuse me, because that's a -1 right there. For part B, let's go through this expression one more time. X squared minus 8 has to be greater than or equal to 0. If you see on here, I have identified that the square root of x squared is the absolute value of x. I don't know if you remember, with the absolute value of x is greater than a number, I'm going to say 3. Then what that does is it causes an or inequality, where if I have the absolute value of x is less than a number, I'm going to say 5, that causes an and inequality. So that's from filling in that information. So absolute value greater is an or, less than is an and. And that's important because if my absolute value ends up being greater than 2 square root of 2, then I have 2 distinct regions that I'm going to be working with. And on this one, we have an added new domain restriction that what's in the denominator is not allowed to equal 0. So I did not put an equal sign right there because your denominator is not allowed to equal 0. But then this turns into, when we do our work, the absolute value of x is less than 2, and that turns into a situation like I mentioned here. For the level 4 problems, it's really putting everything all together at once. For 4a, we're saying what's in the denominator again, not able to equal 0, so I don't have it there. But it's also underneath the radical. So our combination is just 9 minus x is greater than 0. And then solve the inequality, and we get negative infinity to 9. For part B, we got a couple different things going on here. First of all, the denominator, if you solve it, x is not allowed to equal either positive 5 or negative 5. Okay. Second thing, if we do the square root, or that radical portion of it, we will get that x is greater than or equal to 4. So our challenge is, how do we put that all together onto one graph? Well, this is where I graphed it out. So negative 5 is not a possible solution. 5 is not a possible solution. And then what you see in blue here is x has to be greater than or equal to 4. So all together, we're going to say this negative 5 doesn't really matter because everything combined together into one expression goes from negative 4 to 5, but then a break, and then from 5 to infinity. Here's the way we write it in our set notation. I'm not sure which one you would prefer on this. I would accept both. Then for part C, this one I like to do numerically, where if I test some values, say if I test 0, 0 minus 4 over 0 minus 7, negative 4 over negative 7 is a valid number, so this would work. 4 is what I consider a boundary point, that if I plug in 4, I will get the square root of 0, which is a true number. So that would be 0 over negative 3, which is 0. If I plug in 5, I will get the square root of 1 over negative 2, which that's my first imaginary one, so it doesn't work. 7 I can't plug in because my denominator cannot be 0, but any number bigger than 7 is going to be valid. So what's going to work here are all numbers less than or equal to 4, or all numbers greater than 7, as shown by that. What's really happening is, in order for us to get a square root of a positive number, we either need to have a positive over a positive as a fraction, or a negative over a negative as a fraction. Page 2, so part 1 is complete. Part 1 is you understand how to work with domain. Part 2, I'm going to be doing a combination of domains. So in combination of domains, what I need to look for in this situation is what happens to each individual function at the beginning, and then what is the overall result. So we have a slightly new notation, which I'm personally not a fan of, but nobody asked me. So I would prefer to just write it as f of x minus g of x, but I'm at least showing you the notation. What this says is we will take the first function, subtract the second function. Pretty straightforward in that approach to it. Now, in working with it, there's definitely some math that comes out that we're going to have to focus on and pay attention at that point. So if we take this minus this, then what happens is, don't forget to distribute that negative to both terms. So it becomes a negative 9x and a positive 2. So my overall result is negative 5x minus 3. Now I didn't show it here, but the domain of the f function is all real numbers. The domain of the g function is all real numbers. That is because both of those are linear functions. Linear functions have end behavior that goes on forever in both directions. So linear functions have a domain of all reals. And altogether, we end up with another linear function, so the domain is going to be all real. The second thing I asked you to do on this is multiply those together. I'm assuming you guys know how to FOIL. So first, outer, inner, last. This is kind of a combination of the outer and the inner. And then the last is positive 10. This is now a quadratic, and oh, guess what? The domain of a quadratic is all reals, so there's my limitation. Or, excuse me, no limitations on that. For number 3, if I do f divided by g, for f divided by g, suddenly I have a rational function that results from it. So rational functions end up giving us a new domain issue, meaning the denominator is not allowed to equal 0, which is why our domain of negative infinity to 2/9 and then from 2/9 to infinity. For part B, again, somewhat straightforward, where you have this quadratic minus this quadratic, which yields a new quadratic. The domain of this quadratic is all reals. The domain of this quadratic is all reals. We end up with a new quadratic, which domain is all reals. When we multiply quadratic times quadratic, we end up with this quartic, and we could see the foiling process. First, the outer ends up coming from these two multiplied, or sorry, the negative 2x cubed comes from these two multiplied. So, but we could do first, outer, inner, last. In the end, I just put a simplified result there. And the domain of a quartic function, which is what this is all real numbers. And like before, if we divide them, by dividing them, we're creating a new issue that your denominator is not allowed to equal 0. And so what I did was I set my denominator not equal to 0, and then solve for that. Add the 3 to both sides, take the square root, and include both the positive and negative case. On to A. When it comes to radical functions, the first thing I'm going to look at is the domain. So the domain of this one, if we set what's inside greater than or equal to 0, x has to be greater than or equal to negative 1. Same thing here, x has to be greater than or equal to 3. Now, as we combine both of these together, I'm going to pause this. Okay, now that the announcement's done, when we have radical functions, with these radical functions, we have to keep both domains in mind at the same time. And I remember you guys did this, and it was either algebra 1 or algebra 2. So if negative 1 is here and 3 is here, where is it equal to both, or where do both exist at the same time? Greater than negative 1, greater than or equal to negative 1, and greater than or equal to 3? That would be just greater than or equal to 3. That's the overlap of those two graphs. So as we go through the domain of all of these, we are starting from the idea that x has to be greater than or equal to 3. So when we do our subtraction over here, by subtracting them, does it change anything? Not really. There's no simplifying that we can do. So therefore, it's just from 3 to infinity. If I multiply them, you could leave them this way, you can combine them together. The one caution is if you combine them together, it really changes the domain and you can't. The domain still is from 3 to infinity. And then the same thing if we divide, by dividing by that square root of x minus 3, what changes here is this 3, we now have a parentheses here instead of a bracket because your denominator is not allowed to equal 0. So denominator not allowed to equal 0. For part B, what I like about this problem is when I subtract them, I'm going to get -5. So it doesn't matter what I plug into this equation, it's going to equal -5, except x is not allowed to equal 0. X is not allowed to equal 0 because it breaks your original function. So even though this is a simplified answer, it only works as long as x is not able to equal 0. For part B, if you multiply it through, keep in mind when you're multiplying, numerator times numerator, denominator times denominator. We can write that as 3 over 1 and 8 over 1. Multiply it through, and we are going to get this expression. And this one still shows that x is not allowed to equal 0. For 3, if we divide them, we create a new expression, which I call the fraction within a fraction. What I do is I multiply by the least common denominator of my inner fractions over itself. And when I distribute it through, x times 3 is 3x, x times 4 over x is 4, x times 4 over x is 4, x times 8 is 8x. So I now have this expression right here. And that expression is simplified, but domain, x is not allowed to equal -1/2 because of my denominator. But don't forget, x is still not allowed to equal 0 because that was part of the original domain. For my level 3 problem, 3a, I think what more difficulty is because we are now working with combining fractions together. So this is still a bunch of skill review. We're combining fractions together by subtracting. And whenever we subtract two polynomial fractions, or rational fractions, then we have to have a common denominator, which I showed here. We multiply by x minus 1 over x minus 1, this one by x plus 2 over x plus 2. And so when we subtract them, don't forget, we have to distribute, and we're going to distribute the negative to both terms, which is what I showed in that step. Now, I'm a big fan of keeping your denominator factored, because if your numerator factors, then we can reduce it and simplify it. In this case, it doesn't, but I'm a big fan of keeping the denominators factored. Feel free to multiply them out if you wish. Now, our two restrictions show up in this denominator. X is not allowed to equal either one of those. And that does really come from the two original domains. For part 2, multiplying, I would like to say this is more interesting. The numerators multiplied by x, the denominators, those factors, I just leave them factored. And again, x is not able to equal either one of those two values. For part 3, when we divide fractions, suddenly we have a little bit more interest. And then say if we divide by a fraction, it's the same as multiplying by the reciprocal. So if I multiply by the reciprocal of that denominator, and then I multiply through, and I get this expression. So this expression right here shows us that x is not allowed to equal, and I'm going to change my color here. X is not allowed to equal 0 because of that factor. X is not allowed to equal -2 because of that factor. X is also not allowed to equal 1 because that's part of the original domain issue. So fortunately, the algebra simplified some things improperly, but we keep it in mind. And for part B, there's really a lot of the same ideas, just the math gets more and more complicated. So common denominator, I kind of showed this in one step just because I've done this many, many times. So by multiplying by the LCD, we have, for this one, we have to multiply by 2x plus 4 over 2x plus 4. For this term, we have to multiply by x plus 1 over x plus 1. And what I'm about to highlight in green, this is my overall result of that. We simplify the algebra, we get right here. Now in the end, x is not allowed to equal -1 or -2, which -1 shows up in that domain, -2 shows up in that domain. For part 2, you multiply them out, and really there's not a whole lot of simplifying you could do, unless you really want to multiply them together, which I don't. So x is not allowed to equal -1, and x is not allowed to equal -2. For part 3, divide. Once again, divide by the denominator means I multiply by the reciprocal. Combine those together into one expression. And our overall domain, x is not allowed to equal -1 or -2 because of what we've established previously. But x is also not allowed to equal -2/3 because of our new denominator issue. So phase 2 is complete of what I want to talk about. Phase 3 is about average rate of change. Average rate of change is a fancy way of saying slope, but it's really slope in a real life context. So if you're talking about driving, if you go so many miles in so many hours, you could say miles per hour, which is your average rate. If you have a business and you want to establish what are your sales per hour, then you could say from this hour to this hour, what is my average number of sales per hour? I've been talking too much today, apparently. So, average number of sales per hour. Basically, real life context, what is your average change? Mathematically, we look at this as slope, and it's a slope between 2 points. A lot of times you're going to see this as slope on an interval. That interval we tend to write as one number to another number. This is interval notation to say we are starting at the x value of a and we're ending at the x value of b. So if you look at that, if the x value is a, the y value is f of a. If the x value is b, the y value is f of b. So our slope is going to be y2 minus y1 over x2 minus x1. So f of b minus f of a over b minus a. Now this is known as the slope of the secant line. That average rate of change, if we draw a secant, and a secant is really a line between 2 points. If we draw a secant between those, the slope of the secant is your average rate of change. So your slope is your average rate of change. Now what I've done here is I've said with my average rate of change being the slope, I don't feel like we should do this process because the slope of this line is 0. However, I like to take easy examples and I like to show the new process with it to come up with our overall average slope. So what I did was I have these two x values. So I started x equals 4 and I ended x equals 7. So I take f of 7 minus f of 4 over 7 minus 4. F of 7 is 6 and f of 4 is 6, which I plugged in. And so I get an expression 0 or 3 or 0. For this one, the average rate of change on a line, -3x plus 4, is going to look something like this. The average rate of change is going to end up being the exact same slope anyway. But once again, I like to show this average rate of change process. F of b minus f of a over b minus a. F of 3 is -5. F of -2 is is 10. And then that simplifies to, surprise, surprise, -3. So that means the slope of the secant line is actually the value of is the same function. For this problem, -2x squared plus x, I like to draw this situation out a little bit. So this is what the graph generally looks like. And then this is the interval from the x value of -1 to the x value of 2. So from this point, what is my average slope? F of b minus f of a over b minus a. Do the math, and we get -1. So this is the first time that I'm now going to say I don't just want the slope. Let's find the equation of that line. So the equation of that line is going to be y minus y1 equals m times x minus x1. Or I could have used that other point, 2, -6, and I could have gone from there. For this problem, I realize I didn't write it down, but anyway. For this problem, now we're introducing a newer idea. And the newer idea that I have here is, what happens if I'm starting at an x value and then I'm going to an unknown x value? So if I'm starting at an x and going to an unknown x, what will happen is I will begin at this x value of 1 and then go to an x value of what I'm going to call 1 plus h. Now this x value of 1 plus h is really about how much farther away from my beginning value am I going to be? So if I start at 1, I'm going to end at 1 plus some value. So what does that mean really? Suppose I go back to sales per hour. What happens if I want to know the average number of sales from the first to the 3 hours later? So that'd be 1 plus 3, which is 4. What happens if I wanted my sales for 5 hours later, for 7 hours later, for 10 hours later? What I'm doing is I'm building an actual expression here. That expression, when we do the math and simplify it, is 3 over h minus 1. So I'm assuming you guys can work through a lot of that math. I'm not saying it's like easy and it's fast, but that expression 3 over h minus 1 is special because that 3 over h minus 1 represents the slope from the x value of 1 to any h units later. In this case, I wanted h to equal 2. So if h equals 2, I can then plug it in right here and get 3 over 2 minus 1, which is 3. Now, that expression is nice because h is not allowed to equal 0, but what happens when h gets closer and closer and closer to 0? That is what I'm showing in these problems here. This is a lot of the same thing, saying I'm taking y2 minus y1 over x2 minus x1, but I'm doing it with smaller and smaller intervals. What I want to say in this case, h is 1, h is 0.1, h is 0.01, h is 0.0001, which is basically how far away from the beginning value to the next value. So if you notice, all of these, when I do the math, end up being -4 no matter what. And that's because, hey, this is a line, and a line's not going to change its slope. However, on this radical function that I have here, on this radical function, when I go through and I do the numbers, then what you see is this average slope gets closer and closer and closer to what is called the instantaneous slope. So the instantaneous slope ends up being, for this problem, 1/4. And we can see that right there as that decimal, but our instantaneous slope is 1/4. What that means is on this graph of the square root of x plus 3, at x equals 1, which is right here, this slope is 1/4, and that is what we call the tangent line. So the slope of the tangent line is what happens when h gets smaller and smaller and smaller. So this expression that I have right here is powerful because it gives us the average slope for any h, and it helps us approximate the instantaneous slope if h was 0. We know it's not allowed to be, but if h is 0, we can plug in 0 to that new expression. And that's what this goes through. This goes through that process that what happens when our secant line goes between these 2 points, and then between these 2 points, eventually the secant line is going to become the tangent line. Now we're using these points x and then h units away, giving us f of x and f of x plus h. And this is called the difference quotient. The difference quotient, I don't think I actually wrote that there, my mistake. So difference quotient, that is a very, very important aspect of mathematics, mainly calculus. So this is the slope, f of x plus h minus f of x over h. But this new notation, this limit, is what I showed up here, that h gets smaller and smaller and smaller. Now, in the end, what I have here is a lot of tedious math. 100% agree with that. So with the tedious math, what our goal is let's go ahead, plug in these expressions, f of x plus h minus f of x over h, simplify what we get. And our goal is to simplify that h over h, where h is not allowed to equal 0. We could pretend it does, so we can see what the instantaneous slope is. If you see here, f of x plus h minus f of x over h. F of x plus h is right here, minus f of x over h. Simplify the algebra, and this time I get an expression that's based off of x. With this expression based off of x, what ends up happening is that now, based off of any x value that I have, that x value I could plug in to figure out the slope at that point. Visually, if I have x squared plus 1, which looks like this, at the x value of 3, which is about right here, it tells me I have a slope of 6 because 2 times 3 will give me that slope of 6. For 2a, f of x plus h minus f of x over h. Simplify, simplify, reduce the h's. We get this expression, and again, this expression is, this is the slope of the tangent at any x. We want to know what happens at the x value of 1. Since we want to know what happens at the x value of 1, if we plug in 1 right here, we will get 3. And now I'm asking for the equation of the tangent line, which I think I should have done up here too. I did, actually. But find the equation of the tangent line. So that means I need a point. And what I did was I took this x equals 1, and I plugged it in, and I got f of 1 is 0. And that's how I created the tangent line. Y minus y1 equals m times x minus x1. Same thing here. We've had a lot of fractional practice, so I'm going to assume that you can go through and do the work on that one on your own. This one, again, is some more fractional practice. F of x plus h minus f of x over h. This time I'm multiplying by a little bit more complicated denominator, and I'm very happy about that because I'm a math teacher and I love it. So simplify, simplify, simplify. The h's reduce at this step. Let me show that. I'm going to do that in a different color so you can see it. So the h's, if I factor out the h, I'm left with negative 8x plus, or not plus, minus 4. So if I reduce the h's at that point, that's how I get, that's 4h, excuse me. And then get to here. And overall, my simplified expression is negative 8 over x cubed when I plug in 0 for h. I didn't necessarily show that here, but that's going to be minus 0. This will be, this is x minus 0 squared, which is just x squared. And then for this one, same thing, f of x plus h minus f of x over h. What's special about the approach I took at this one was I multiplied by what's called the conjugate. If you notice, those terms are the same, but I put a plus inside of a minus. You guys did this in Algebra 2, where if you're trying to rationalize a denominator of the square root of 3 plus 1, you multiplied by the square root of 3 minus 1 over the square root of 3 minus 1. So that idea of a conjugate kicks in here as well. And then when you multiply it through, the outer and the inner cancel each other out, and the square roots cancel each other out, which is why we multiply by the conjugate. Simplify, and look, those cancel out. And now, if you follow, I plug in 0 right here, and I get the same expression in the denominator. So this is my equation for the slope of the tangent at any given x value. So once again, this is the slope of the tangent at any x value on the graph. And if you notice up here, I plugged in the point, and that point is what I used along with the x value of 3 to find the slope. So the point slope form is what I have. Hopefully you've understood and enjoyed the video, and I will see you next class. Bye.